And since this is remote, this is my second class, actually third class teaching remotely, but still this is a different class. So I'm going to experiment with a few things. So please offer me suggestions on how to improve things for you and for me. Okay. So the first lecture will be partly by presentation. Okay, hold on. So why am I not able to? Okay, I think this is better just because I want to still be able to see our faces while presenting. Okay, so what this course is called Algorithmic Machine Learning, and well, did something happen? Sorry about that. There's some problem with my earphones today. Okay. So this course is called Algorithmic Machine Learning. We'll have lectures 10 to 12 on Mondays and Wednesdays. And the main resource for the course will be the class website. Start from there for everything. And I'll have office hours on Wednesdays from 12 to 1. I'm losing audio connection. Give me a minute. Okay. Okay. And so first, what this course is, it's going to be mainly about a few algorithms, just a few handful of algorithms, and their applications. So it's roughly divided into 6 parts, and each part covers, one algorithm and its variants and things like that. And what this course is not is, it's not a pure machine learning course, in the sense that we won't be putting much emphasis on building models and trying to decipher where models are coming from for the most part. We will address some of these issues, trying to look at the motivations and so on, but we won't dig deeper into them. And we will also not dig deeper into when these models would work in practice, which is again a very important question, but that's not something that we are going to look at in this particular offering. And another thing is that this course is not about the latest tools or software inventions, which are amazing that are happening in machine learning. Right? What this course is it's a way, or at least my hope is that you'll be able to design the next generation of tools by understanding what's kind of beneath the box in many of these tools. Okay. And in terms of prerequisites, there are 3 main prerequisites for this course. It's hard to quantify what level is needed. There is 3 sort of rough components which are very important to understand the basics of. One is linear algebra, the other is probability theory, and classical algorithms. And all 3, at the typical undergraduate course level, you don't need to know something sophisticated like measure theory or fancy conditional expectations and things like that. They might show up later on, but by then we'll build up the background necessary. But you need to know stuff like, what's the dimension of a subspace, what happens when I project onto a subspace, what is the expectation of a random variable, what is the variance of a random variable. And for algorithms, like, what is the time complexity of an algorithm? How do you quantify that? What is big O notation and things like that. So for instance, for algorithms, the undergraduate equivalent at UCLA would be CS 180. And there's an assignment 0 on EdSTEM that's been posted on EdSTEM. Please take a look at that, just to get a sense of what might be expected going forward. And once again, it's not a hard requirement. If something is not clear from the assignment 0, don't panic. You can talk to me about it, and we'll see if there's something in your background which will still be relevant and will be sufficient. Any questions about this? So when I'm on this presentation mode, I'm unable to see chat. So if you want to chat, then chat with me. Then just unmute yourself and ask questions. Okay. All right. And in terms of logistics, the main resource for the course will be EdSTEM, which is just like Piazza, but I think it's a bit more sophisticated and more suited for our purposes. We'll use EdSTEM for communication. I want you to ask a lot of questions and have many offline discussions between with each other and myself. And I'll also share some Python notebooks for you to play with and hopefully to demonstrate some of the algorithms, sort of just toy examples of what we are doing. And for assignments, we'll use Gradescope. And when I can, maybe I'll use some programming interface, but for the most part, we'll just use Gradescope. And the website, which is again kind of a launching point for many of these other links, we'll have the Zoom link, a link to the shared whiteboard that we will use for the course. And office hours, as I said, are Wednesdays from 12 to 1. And in terms of grading, there will be 4 assignments for the course, each covering 4 lectures. These are the dates that they go out. The first row worth 18 points, the last row worth 17 points. Again, they're all released from Gradescope and are due after a week. And there will be a final, which covers all lectures, so it's cumulative and will be released in the finals week. I'll decide on the exact date and format after getting feedback from you. My intention is to have like a take-home exam for a week, but it'll depend on how things are going, and if you have any suggestions, they're very welcome. It'll be 25 points. And since it's a remote class, I found that it's hard to get students somehow get to participate. So here's my way of trying to do that, which is give 5 points for class participation. This can just be asking questions of if something is not clear during class when you're attending class in session, or if you're not attending in session, you can still ask questions on EdSTEM, and in the end, I'll just make a quick tally of how much each person is participating. Any questions about the grading or the logistics? Okay, so if there are no other questions at this point, so let me tell you a little bit about what this course is about, right? So the course, I think, is going to be a lot of fun, at least for me, because it talks about, it overlaps a lot with my core research area, but not deep into it, kind of, the basics, but pretty somewhat refined level. So the first part, which will be kind of a running thread throughout the entire course, will be the perspective of viewing learning just as optimization. And we'll keep coming back to this perspective again and again. So here we'll first talk about what learning is, again at a very rudimentary level, because we're not focusing on how to model learning. We are focusing on, suppose someone already did all this work, how do we actually as computer scientists solve this computational problem? And here we'll focus on sort of the main algorithms, which is gradient descent, stochastic gradient descent, accelerated gradient descent, their variants and their applications in the first 5 lectures. So we'll dig deep into these algorithms, we'll give rigorous guarantees when we can, and we'll also see some places where they would fail, which is also important to understand. In the second part will be low rank approximation, or if you're familiar with the keyword, principal component analysis, and which is again used a lot. And here, once again, typically you'll see this covered in maybe a lecture in many other courses, but we'll do kind of a deep dive here, try to understand when it works, why it works, and what are the algorithms that, let's say, your favorite software uses when I ask it to do principal component analysis or singular value decomposition or things like that. And then we'll talk about online learning. Here the problem is that you're trying to solve is, you have to make a prediction on the fly. You see some data, you have to make some prediction now, and then tomorrow something else comes up, and so on. And this part will especially tie in very well with part 1, and hopefully we'll get to explore some of that connection, which is really beautiful. The last three modules are somewhat more advanced in the sense that they are based on more current or things that have been developed in the last few years. So one is graphical models. It is a topic that I am personally very interested in terms of research in the last few years. And the last one is robust inference, where you are trying to defeat corruptions or outliers in your data. Okay, so that's the rough plan for what this course is about. So module 4 and module 6, I'd say, are probably topics that are most current. And module 5 again is kind of a classical topic from computer science, algorithms literature, but I think it's getting more and more important in machine learning as well. So that's the rough outline of what the course is about and the structure of the lectures. Okay, so for the lectures themselves, for the most part, we will use this whiteboard.
Professor?
Yeah.
You have a Zoom background on, so we can't see the whiteboard.
Yeah.
So, you just brought it up. My apologies.
Yeah. Yeah, so I'll share it because somehow it would be nice if I could show it, but I haven't found a good solution for zooming properly onto the whiteboard. Sometimes I'll try and do this, but as you can see, it kind of flickers and so on. So I think it's better off with the board.
I see. Okay. Thank you.
Yeah, so I still haven't found out a good solution for the camera to not flicker and make it kind of a nice visual. Okay, so we'll use this to write down notes. You can, I shared the link for this on the course website. So you can follow it, you can scroll around on it irrespective of where I am. And if you lose me at some point, if you click on the icon, my icon there, then it'll go to where I am writing. And the plan is to have one shared notebook or one whiteboard for each module or segment of the course, and each lecture will be on an individual sheet. Okay, and the PDF export currently doesn't work quite as well, but I'm working with the people who are designing the software to try and improve it for the course. They said they realize a customized version soon. And the other thing that I want to show to you is the other thing I wanted to show you is the EdStem platform. Okay, so this is the EdStem platform that we will use. So if you go to the different sections here, one is discussion, which is where you'd ask your questions. The other is workspaces, where none of these things are public now, but you'll see some things for you to play with later on when the corresponding sections come. I'll release them as we need. I don't want to confuse you by releasing things too early. And then this is not student's view, but this is my view. So if you go to each lecture, there will be things like this. So for example, each lecture will have sections. So today's slides are here, the transcript, the video. Once it's ready, I'll upload it on YouTube and embed the link here, and also assignment 0. So this is something that I want you to look at after the course, after today's lecture, just to get a sense of background required. So for each lecture, I hope to have all this information available under this lectures tab, under this lessons tab. Okay, and you must have received a registration email if you're already on CCLE for the course, and if you're not, then let me know. It's very unlikely that I'll be giving out PTE numbers for the course, but there may be a few exceptions. So let me know. Any questions about that? Okay. All right, so let me now go back to here. Okay. All right. So now we can start our actual lecture. Enough about the background and the setup for the course. And now let's jump into the topic. Okay. All right. So even though I said that for the most part we won't be talking about what learning is, I do want to spend roughly half a lecture trying to discuss the basic model, which will be important for us, right? So what is learning? So in machine learning, can you give me some examples of the tasks that you'd associate with machine learning? Things or applications that you might have. Any suggestions?
Image classification?
Sure. So let's think. So what is learning? And some examples. So image classification, that's definitely an important one. And in fact, one of the cases where we've had amazing successes recently, and which is driving much of the latest applications. Any other things? Just whatever comes to mind.
Predicting if someone has a disease or not.
So let's say predicting morbidities. Anything else?
Machine translation?
Translation, definitely.
A lot of probability and statistics applications.
Sure, so let's say maybe statistical inference. It's a kind of broad area, but definitely fits into this. But you can also think of more concrete things which you might not realize are actually driven by machine learning, right? So can you think of something that you take for granted but really are driven by machine learning stuff? And something that has been in the news a lot recently, right? So your news feed on your favorite, Facebook, Instagram, whatever. Right? So you might think there's like a fixed thing that you're seeing, but these are actually driven by algorithms behind the surface. Anything else?
Your recommendation system is that?
Definitely, that's a very important one too.
Advertising falls under this category too.
Yes. So recommendation systems, think of movies, friends, possible connections, and things like that. And advertising is also almost related to recommendation systems, right? But it's a slightly different problem. There's a different component to advertising, which is not present in recommendation systems, but it is a little bit like I'm trying to recommend what product for you to see.
Is the NLP considered to be one of the learning examples, the natural language?
Yeah, definitely, right? Again, machine translation, you might think it doesn't seem much like learning, but how you get to the translating software is through learning. And that's a topic that we won't address, but all of these are definitely applications or of machine learning algorithms. Okay? And you can see that there's just so much variety here, right? You're talking about biological data here, you're talking about images, you're talking about just text, and you're talking about recommendation systems, it's not even clear what you're processing there. What's the input, what's the output? It's not even clear what's underneath the surface there, right? So these are applications. Now let's think of some categories of machine learning. So what do these fall under? By categories, I mean types of learning.
Supervised.
Right. So supervised is definitely the most important and most well studied. So supervised basically means it's a traditional view of learning, which pretty much we all think of when you think of learning, right? So I give you some data. I'll tell you, okay, here's an image. This is a cat. So this is cat, right? And okay, I'm not going to draw a dog. I'm not that skilled, right? And so I give these images, and after some time, I show you a new image, and you have to tell me what that image is. So that's supervised learning, meaning there is some supervision that happens at the beginning for you to design your labeling algorithm, and then after that, it's completely up to you. And how about something else? What else is there?
Reinforcement learning.
Reinforcement learning is a bit more sophisticated than this, and it's kind of the setting where what you do can change what you see next. Okay, and that's again something that I wish we would cover in this course, but it's not something that we'll touch upon in this course. How about something else?
Unsupervised learning.
Unsupervised.
Unsupervised learning for sure. So unsupervised learning, it's a little bit like bucketing, right? Suppose you have your database of songs, and I just want to categorize those songs into different groups, like, I want genres, right? Okay, this song is in the same genre as another song and so forth. So here there's no labeling that's happening for us. We just have the raw data, and we have to figure out how they are related to each other. Nothing external, but between themselves, how are these things related to each other? And of course, there's everything in between, right? There's semi-supervised learning, where you have some little bit of label data, meaning I give you maybe 10 images, right? And then I give you 1 million unlabeled images and ask you to figure out, okay, tell me what's a cat and dog from now on. You might think this seems hopeless, but you can actually do something like that too. It's not unreasonable. And there are things like active learning, which is the kind of learning that we do, right? There's a course, this is what I'm doing now is supervised learning. But then you come and ask me a question based on what is unclear to you, right? So you're actively seeking out what's the next bit of information that would be most useful for you, right? And there's a question, can all unsupervised learning be considered clustering, or there are non-clustering unsupervised learning? Almost like clustering. Sometimes it's not clustering, but you can think of it as clustering, but not in some high dimensional space, right? If you think of something like word2vec, it's learning a representation of your word as a vector. So it's not exactly clustering, but it's not a finite number of classes, but it's still learning a representation. It's reducing that word to a single vector. Okay, that's a good question. So there are many forms like this, and for the most part in this course we will focus on supervised learning, and we'll spend a few lectures on unsupervised learning. But as I said, supervised learning is very important because it drives many of the latest applications, and even if you're doing unsupervised learning and so on, at some point you will end up trying to do supervised learning.
Professor, can you elaborate on active learning a little bit more?
Sure. So basically active learning is a setup where, imagine you're trying to build an image classifier, right? And you have a few images that have been labeled. and you have like tons of unlabeled images. Unlabeled images are so easy, right? I can just download, all the thousands, billions of images on Google, but no one's labeled them. Okay, this is a cat, this is a dog, and so on. And so what you do now is, okay, so I have this 10 images, but now I have this weird image that I'm not sure, right? I try to figure out, imagine you have to pay $1 for every person, every labeled image. So I go to someone and say, okay, can you tell me what this image is? So if I'm paying $1 for every question that I ask, I should probably choose my question in an optimal way, right? So if I'm trying to learn cats and dogs, there's no point in going in and asking, okay, is this a mountain, right? So I would try and ask something which is most informative for me. And in active learning, part of the algorithm's job is to try and figure out which question to ask next. Okay, it's a whole area by itself.
Okay, thank you.
Okay, there's a question, is self-supervised learning another category? That's a very important thing too, and I mean, you can think of it as something between semi-supervised and supervised, but it's very new category in some sense, right? There are self-supervised learning has shown to be very useful in practice nowadays, but you can think of it as some subcategory of semi-supervised learning. Okay, so there are all these different forms of learning, right? So let's start with supervised learning and build the most basic model. What does it mean to have supervised learning? And we are going to talk about things running on the computer, right? So if you want to do that, let's first we have to be very quantitative about these things. You can't just say, okay, here's an image, tell me whether it's cat or dog, right? The computer, remember, only sees zeros and ones. Or at a more abstract level, it's only going to see numbers, right? So everything has just numbers, there's nothing else. So we had to quantify this in a very we have to do it in a very precise way. Okay, so let's try and do that. So how to model supervised learning. Okay. So first, if you think of learning as an algorithm, every algorithm has an input and an output. So what should the input be here?
I guess the data and the training labels that you have.
Exactly, right? So its input is some domain, really, right? Nothing else, some domain that we have. And when I can, I'll try to denote it with this calligraphic X. So the domain is very arbitrary, right? So it can be pretty much anything. And the input is elements from some domain, right? So this could be images, documents, user profiles, browsing history, whatnot, right? Voice recordings, if you think of machine translation software, or text recognition, or audio to text translation, it's just audio recordings, right? So all of these things can be parts of the domain, okay? And then the other component in supervised learning is labels, right? I want to tell you what each element in this domain is at some level, right? So it could be cats, dogs, foxes, or etc. Right? Or it could just be something simple or numerical, like 0 or 1. Right? Is this a good image? Is this a bad image? Is this document in English? Is this document not in English? Or something silly like that. You can also have, maybe cancer, diabetes, and things like that. And you can also have labels which are not necessarily discrete, right? So for example, you're measuring something for each person, right? And it could also be like, maybe weight, height, cholesterol, right? So actually, let me write it differently. It could just be real numbers, right? Maybe a number between 0 and 1, maybe a number between like an integer or whatever, right? All of these are labels, okay? And what we will always work with is the fundamental building block for us would be a data set. What is called a data set, which is now commonplace enough that we can just write it as a single word. And what's a data set? For us, it's a labeled data. So meaning I have x1, comma y1, x2, comma y2, so on. Okay. So here, these are elements from the domain times the label. So the labels are coming from some domain, either just cats, dogs, foxes, and so on, or 0, 1, or digits 0 through 9, or just real numbers, right? And so the data set is just a collection of tuples. This is what you're given as input. This is the labeled data set. And I have x1, y1, x2, y2, up to x and yn. And for the most part, I'll try to be consistent throughout this course, and we'll use statistics notation in the sense that we'll use n as the number of samples or the size of the data set, and we'll use d for dimension of where these things are coming from. Okay? So this is our input. What is our output? What is our goal later on? What are we trying to do here? So what computational task are we trying to solve starting from here?
We want to find the mapping from the domain to the set label, such
Exactly.
that the error is minimized.
Right. So our goal is to, given a new test example, I'll say predict. So that's our goal. Our output should be an algorithm, right? It's not to, we don't have a specific test, sorry, it's not text, it's test. Specific test example on which we're trying to predict the label, right? Our goal is to design a prediction algorithm, right? So we want a way to do the prediction. Some object which now, whenever given an image or given a new element from the domain, outputs a label, right? So remember that we are not given the test example as part of our goal. Our goal is to design this prediction mechanism, okay? And we want this new label, this new prediction to be accurate, right? It should be good as far as we can tell, as good as possible, okay? I mean, this seems reasonably quantitative, but is this a meaningful question that we can try and start solving? What do you think? Can I just, if this is my setup, can I solve any problem? Well, there's a huge shortcoming here, right? The test example that I'm saying is coming from the domain could be completely unrelated to my data set. Right? So this is impossible as stated. So there's a huge difference between what the domain is and what the test set is, or what the training set is, right? Imagine I give you only images of cats and dogs, and for the test example, I give you an image of a fish and ask you to tell you, what is it, what kind of fish it is. Obviously, you're not going to succeed, right? Because you haven't seen anything like the test example. So this seems like, we're still not there at a rigorous quantitative computation problem that we can just focus on solving. So what is missing here?
Assumption about the test set.
Exactly, right? So we need to make some assumption about the test example X being somehow related to the training data set. Okay? So let's call this training data set D. And what's missing is that at the very least, we need an assumption about how new examples X relate to D. Actually, let me not use D here. To the training set, right? So we need some connection between these two things. Otherwise, there's no point, right? If I just show you something completely unrelated to what you've been trying to train on, imagine I teach this entire course and in the final I show problems on number theory. It's not going to be a good experience for anyone, right? So we need to make some assumption about how the new examples relate, new test ones relate to the ones that we already saw in training. And how do I model this relation? What's a nice way to model this relation between the two?
Do we claim they come from the same distribution?
Exactly, right? So all of this is kind of leading you to the most fundamental model that underlines most of machine learning. This is not the one that really drives many of the applications, but I think it's the most basic one. I mean, it's not the one driving the applications just because it's something very much too lenient, but it's the starting one. It's the most basic one and widely applicable one. Okay? So how do we relate these two things? And the assumption number one is that there is an underlying ground truth distribution on training and test examples. Right? So the assumption is that there is some distribution D on X, on the domain. There is a distribution on images, right? And each x1 up to xn is an independent, identical sample from okay? There's some underlying distribution, and the test examples are also drawn from the distribution D. They're independent of the training ones, and it's just another independent draw from the example. Okay, does this make sense? This is an implicit assumption that pretty much any learning algorithm has to make. Okay, so this is an assumption on just on the domain, the examples that we are seeing, right? It's not on the labels. We haven't said anything about the labels so far. So let us now address that. So with this assumption, it almost makes sense, to ask for this holy goal of ours, which is to, given a new example, predict the label. But is this sufficient? If I tell you there is some underlying distribution, is this by itself enough for me to go back and solve the computational problem? What do you think?
I don't know.
Yeah, go ahead.
Well, cause like with law of large numbers and stuff, like even if you just sample, it's possible that the training data and the test data will still have like a different distribution. So
Well, so we'll be working with enough large things that even though they might have slightly different distribution, I think on average they'll start looking similar enough for us.
okay.
So like imagine like you see 1 million images, then the next 100 would probably look something like what we saw before. That's kind of an underlying assumption that we are willing to make, and as far as assumptions in machine learning go, that's one of the probably the least controversial ones.
Good.
Okay, but there's something else, right? Where are these labels coming from? That should be worrying for us, right? So in some sense, if you think of each image and the associated label as being generated by something, what makes you think that given a new example, I can predict its label? Would it be possible always, no matter how the labels are chosen?
No, that you could just have like a random thing.
Exactly, right? So some of the labels also have to be limited. So far we put a restriction on how the examples are coming from. Now we have to also put in a restriction on where the labels are coming from, right? So the labels somehow cannot be completely arbitrary or very, very powerful. Okay? So that's the assumption number 2. Is that the labels, the way the labels are being generated, cannot be arbitrarily complicated. Right? So labels cannot be arbitrary. Okay? So the way this is quantified is that there is a class of functions or hypothesis class which maps from the domain to label set. Okay, this is not a single function, it's a class of functions, right? You can think of maybe each person is in some sense like a function, right? Give me an image, I'll tell you what the label is. But my mapping might be different from your mapping. So each one of these functions could potentially have different behaviors on your data set, right? And one simplifying assumption is that, example, you can say the label yi is f of xi. For some unknown f in my hypothesis class. Okay, there's some unknown function which is generating these labels. I don't know what it is, but there is some unknown function, and we have to assume that this labeling function h is kind of not arbitrary, right? So given any image, I can't just generate a random label and give it to you. Then obviously you can't do any good prediction. And the way this shows up quantitatively is to make a concrete assumption on what this hypothesis class would be. Like you'd assume some simple model for where these functions are coming from. That's a way to limit the how labels are generated, and then we can go from there.
So wait, Professor, so when you say the labels cannot be arbitrary, you mean like the labels have to stay constant for each image, like, and they can't change, like a...
That, and also, I mean, there's something much stronger than, it's an assumption that's much stronger than that. It's saying there's a simple way that these labels are being generated. The ground truth is being generated. Okay, it's somehow, it's not like, every time I see an image, I toss a coin. I keep the outcome of the coin the same for the image. But if it's just random label every time, then I'm not going to be able to predict what's going to come next.
Thank you, Professor.
So that's an important assumption. And often, as we'll see later on, what the hypothesis class is changes from applications to applications, and that's a whole, you have to choose them wisely. Okay? So at least so far, we made some concrete assumptions about the input, right? So where we are is, okay, we're saying there's some underlying distribution D, from which our examples x1 to xn are being generated, and the labels are coming from some function from this hypothesis class. Okay, so let's take a 5-minute break, and when we come back, we'll start talking about, okay, this is our model for the input, but what should my output be, and how do I quantify whether or not my output is good? Okay, so we'll resume at 10:55. So my goal in this introductory lecture is to talk about the most basic model, right? Some of you might have seen it before and it might seem a little slow, but I think it's such an important thing that we should take or look at these assumptions and convince ourselves that, these are pretty natural ones that you end up making. And these are like the minimal assumptions that you end up making. Later on, you might make much, much more stronger assumptions because of how difficult these computational problems are. Okay, so far we made 2 assumptions. They seem pretty natural. And now this is something about the data set, and this defines a computational problem pretty well, or almost, right? So what's our goal next? What would be one way to say, what's our output then? This is how we categorize our input as coming. What should the output of your algorithm be? Any guesses? What would be like the ideal output?
Like the function in the family.
Right. So ideally, I'd say, okay, just tell me what the function in the family is, right? But maybe that's just way too hard, right? Like, do I want something exactly what that function in the family is? Or could I have something which is a bit more relaxed, but still just as useful in practice? Right, so again, think of exams, right? There is, for A, I don't say you have to get every problem right? So there's some wiggle room, and we should allow our algorithm also such a wiggle room, okay? And so that's our third, so let's say, component in our model. So what kind of wiggle room would you like to have?
The function that we output should be close to one of the sort of true functions, but maybe not 100% accurate.
Yeah, exactly, right? So I want to say somehow that it's really, really hopeless sometimes if to say it has to be perfect on every potential future example, right? So there's going to be some error in how well I predict, right? So we'll say error in prediction. Okay, so this is our parameter epsilon. Okay, so think of this as some number which is between 0, 1. You should think of it as something tiny, like maybe 0.1, 0.01, or what have you. But how can I quantify error in prediction? I want to say that, okay, my function what I am computing differs from the true unknown function in some way. But how do I quantify differ?
Is it based on the number of test samples that it predicted correctly?
Yes, so that's exactly what we want to do. But remember that when you are designing the algorithm, you don't see what are the test examples, right? All you have is the training data, and you have to design your marking or benchmark for how good your algorithm is based on something like that.
So is it then going to be, based on the training examples that it can detect?
Right, so it's going to be something like that. And as a first step, what it's trying to accomplish is to guess how well it might do on future examples, right? So Raji, you're absolutely right that that's what we're going to end up doing. But kind of the goal that you're trying to solve is, I want to gauge how well my algorithm is going to do on potential future examples. So how do I quantify that?
We quantify that as a conditional probability.
Right, so maybe I can say something like, we quantify that based on conditional probability, but here's where our assumption about the underlying distribution really comes into play, right? So I don't care, if my prediction algorithm does wrong on images of mountains after training only on cats and dogs, right? I want it to do well on examples from the distribution that is trained on. So if I now generate a new test example from the same distribution that you trained on, I want it to be right most of the time. Okay, so I want to say that, okay, 90% of the time, if I generate a new future test example from the same underlying distribution, then I'm correct. Okay, does this make sense? So this is your error in prediction. There is this f of x, and I want it to be accurate most of the time. And once again, this is a very basic model, so we'll refine it in a few minutes later on. Okay, but this is, you can think of it as a pretty natural score for what your algorithm is doing. There's a question, what is h again? Oh, sorry. So f is the true unknown labeling function. Maybe let me use f star for that, just to make it clear. H is my output predictor, right? And remember, the output of my algorithm is not a simple label. It's a function that computes predictors, right? You're designing a predictor, not just a label. Okay, so it's judging how well my output predictor that I computed based on my data set versus the truth. You might ask, okay, you don't know the truth, so how are you going to measure it? But we'll come to that later. But just as a holy grail, we can say I want this quantity, this probability of wrong prediction, to be as small as possible. Okay? And so you're in some sense learning only approximately, right? And we're almost done with the full mathematical model, very quantitative one, but there's still one catch. And what is that catch? Can anyone tell me what that catch is?
Like maybe some labels are closer to other labels than like for example, for our labels were real numbers, and you had a label of like 0.5 and 0.6.
Right, so that's an important one. So okay, so that's an important one, and we'll address that pretty soon. But let's say, we need to relax this equality. right? So, I mean, if you think of discrete data, if it's like cats and dogs, then okay, you can say, okay, you have to be equal. But if you're talking about predicting like weight, height, or some other number, numerical data, then equality is just like, it's way too strict, right? Then you can start putting some other metric gauging how close your prediction is, right? That's important, and we'll get to that. But there's something a little more sort of first principles that we are missing here. And this is something that we'll just address once, and for the rest of this course we'll take it for granted, but we have to look at what this assumption is. And this is with the fact that, remember we said our goal is to minimize this prediction error, but our training set itself is randomly generated, right? You're getting examples x1, x2 up to xn from some distribution, right? Imagine you have this database of images and you keep drawing images from that at random, and all the images you see are just cats. It's kind of unlikely, but that can happen, right? What do you do then? Can your algorithm succeed in getting a good prediction from that outcome?
No.
No, right? You just haven't seen any dog, so you just cannot, right? But so far, nothing in our model accounts for that, right? Because we say, okay, there's an underlying distribution that can happen and so forth. So this is quantified in a very easy way by saying we cannot expect to succeed always. By succeed, I mean getting within 90% of the true function, right? So this is different from error in approximation. This is completely different. This is like total failure. You only saw images of cats, then you just can't do anything, right? So this is probability of failure. Or what is known, we'll just denote it with the letter delta. And typically you should think of delta as something really, really small, much smaller than the error of approximation epsilon. Right? Going back to cats and dogs example, the probability that you only see images of cats should be astronomically small, unless the fraction of images of cats and dogs is very skewed, which it might be, but who knows, right? And so this entire thing, you can see our goal now is to be approximately correct most of the time. So I want my predictor, my algorithm, to give something which is probably approximately correct, right? So this model or this set of 4 assumptions leads to what is called the probably approximately correct, or PAC model. Okay, so the probably is coming from the chance of total failure over the data set. The approximately correct is saying that I don't as long as my prediction is almost always correct, I'm okay. Okay. So this was introduced by several people. In the statistical machine learning literature, it was kind of developed by Vapnik by can't pronounce the C, Genomics, I think. And in the computer science literature, it was kind of independently developed by Les Valiant, and he termed this the PAC model. So let's write down the PAC model fully. The history is a bit murky, right? In the sense that because it's such a basic one, you can see variations of it in literature for a long time. Okay? And the PAC model is as follows. We'll say that an algorithm epsilon comma delta PAC learns a hypothesis class. So we have this epsilon, which is the approximation parameter. Delta is the probability parameter, and our hypothesis class, which is our assumption on where the labels are coming from. So there's a question which is, can you give an example of what this low chance of failure looks like in a well-known ML system? So basically this low chance is typically so low that you don't see it. In the sense that when, let's say, Google tries to design your labeling algorithm, they have many chances of throwing out the examples where they were failing. Okay? And basically, if you have 1,000 examples, this chance of failure can be made exponentially small for examples. Like typically it's like 2 to the minus 1,000, so you never see it in real life. But in the model, we have it. Just because it is there, even though we don't really see it, we have to quantify it. Okay? So as I said, like, this delta can be made really small. The dependence is basically usually like 2 to the minus n, where n is the number of samples. So the more important one is epsilon. So an algorithm has this chance of failure with sample complexity n of epsilon delta h. Like, I tell you have my algorithm, my holy grail is somehow to say, okay, you give me so many samples as a function of epsilon comma delta. If when I give you input x1 comma f of x1 up to xn comma f star of xn, where xi are generated from distribution D, okay, and f star is some function which is in my hypothesis class H. It's the same function for everything. The question, let me get to the question in a second. And the goal that we want is the following. So this is my input, right? And the output is some predictor, H, okay, that I'm computing. And what we want is that with probability 1 minus delta over the x1 up to xn okay. So the algorithm is kind of random because the data set is random, right? And we're saying given this data set, which is generated from my underlying distribution with high probability, except with this 1 minus delta chance, when I declare total failure, my prediction is almost is epsilon 1 minus epsilon accurate on new potential examples. Okay. So there's a question, do we consider time invariance when describing the PAC model? I'm not sure I completely follow it, but basically here we're assuming that the future examples are coming from the same distribution as the training examples. So if that is what you meant, then we are making such an assumption here. Okay. And the other ones kind of, definitely are important in practice, and maybe the closest we'll get to the case where things can change with time is in online learning, as we'll see later on. Okay, but is this basic model clear? This is like, ML models 1, 0, 1. You say, okay, I'm getting these samples, I want to be accurate on most of the ones in the future, except with some tiny amount of probability of failure where all bets are off. Okay, this seems pretty good mathematically, right? Like now we have a very quantitative task. Given these things, just tell me how to compute this output. Okay, and in this setup, what are some questions that you'd like to address now? So some of you already asked me before, right? Like, here when I said my goal is for the probability of my algorithm to be correct and future examples to be high, how do I measure that? Right? I don't see future examples. All I see is just my training data set, right? So how do I get a sense of what I'm going to do in the future? And you might also ask, do I know this underlying distribution D that I'm trying to learn from? Do I know that distribution or do I not know that distribution? Right? And how complicated is this hypothesis class? And also, of course, there's this algorithmic challenge of how do I even find this hypothesis edge? How am I going to zone in on this prediction algorithm? Okay. So you can see there is somewhat statistical questions here. Obviously, they're all very interrelated, but at a high level, in the most significant bit, I'm going to separate them. Right? One is how many samples are needed. If I give you infinite amount of computational power, can you tell me how many samples would suffice in finding such an edge? How do I argue in this case? That should be the first step, right? Is this problem solvable even if I have infinite amount of computational power? And if it is solvable, how many samples are needed in this case? And the catch here, as I said, is that you don't get to, how are you going to judge how well your distribution is going to do in the future, how well your prediction algorithm is going to do in the future, if you don't know what the underlying distribution is? That's an important thing. So how to gauge error. Okay, and there's a whole theory in statistical machine learning, and there are a lot of mysteries around that, especially for deep learning. And this relates to what is called generalization error. That's the ML/statistics term for what this is. And we won't talk about this much in this course. It's a really, really important thing, but we'll only touch upon this and maybe a little bit in the later topics in the course. Okay. And what we'll focus on is the algorithmic question. And once again, you really can't separate these two things out when you think about them in any deeper level. But as a first step, let's categorize them in this way, which is how to find the best possible edge. Suppose someone told you that, okay, it is actually possible to find this best possible edge using 1,000 samples. Can I now go and find this edge? Okay. And someone also told me that, okay, you're having trouble trying to gauge your prediction error because you're not seeing future examples because they are in the future. But here's a different way to measure how well you're going to do in the future. Can I now go and find this edge? So for the most part, in this course, we'll focus on these algorithmic questions. Okay, is the divide clear at a high level? All right. So now let's start talking about what this algorithmic question is and how we might translate it to something that is a bit more tangible, something that is a bit more computational for us. Right, so right now it's still a bit vague, right? I'm just seeing this x1, y1, x2, y2 and so on. My goal is to find an edge which has small prediction error, but I haven't told you how to find good prediction error or anything like that. Okay, and here's where one of the most important steps and mysteries in modern machine learning is. Which is in the framework of viewing learning just as an optimization problem. Okay. Okay, I should also say that packed learning, as we saw now, is like almost 30-40 years old now. And it's a very good basic model to start with, but it has very strong limitations. And one of the most important ones is that for many interesting models that you care about in practice, packed learning leads to questions which are computationally unsolvable. The statistical questions are very well understood for the most part, but many times the algorithmic questions end up being just not possible to solve. You know, there will be NP hard or things like that, and in which case you really need to find other ways. And we'll address some of them later on in the course. So let me just put that as a remark. As far as goals go, packed learning, being able to do packed learning is very strong because you're not assuming anything about the input distribution D. Right? I'm saying, okay, no matter what the distribution D is, give me a learning algorithm. Right? And it's very strong in the sense that many times the problem becomes unsolvable computationally. Meaning it just becomes NP hard or something like that. You can show that there is no algorithm that will solve this problem in time which is 2 to the n. Right? It's completely hopeless. Okay. The statistical questions are very well understood. We know we have very rigorous ways of going about these things, but the computational questions become unsolvable for many interesting, even simple complexity classes, simple hypothesis classes. Okay? And the ways to go around them, we'll address some of them later in the course. Okay? Alright, so now we are going to start with this packed model. We had this prediction error, probability of failure, data set, and so on. We have this underlying distribution and so forth. But much of modern machine learning started with this as a motivation, but kind of takes a leap to this learning as optimization, and will just stay in this world from this lecture on, at least for most of this course. Okay? So what do I mean by learning as optimization? So what do we have so far? So we have distribution D on X. And you should not assume that we know this distribution. Okay? What we have are really, what we see are independent IID samples from the distribution D. Okay? Because there is probably some underlying distribution on natural images, right? Things that you see in the real world, I mean, not on some modern art pieces, but something that you get out of taking a picture from the real world. We don't know what the distribution is, but we are seeing images from that or samples from that distribution.
So I've been seeing a term called empirical distribution. So what is that? How does that link with our definition of distribution and training distribution?
Right. So that's a very good point. In fact, you brought it at the right time. So we have some underlying distribution that we don't know what it is, right? But we do have samples from this distribution. We have an assumption that there's a distribution from which they're being sampled from. And empirical distribution just means this guy. For the future, if I just output a random xi from my data set, that's a new distribution, and that's called the empirical distribution. It's in some sense supposed to approximate my underlying distribution. Okay? And it's called empirical because it's kind of generated from what you see or what you've seen so far. Okay, that answer your question?
So can we write a density function about the empirical distribution? Say, are we assuming that the distribution over the samples are uniform when we talk about empirical distribution?
So often that is the case. We can't really write a density function because it's a discrete distribution, right? There are only a finite number of points. Your underlying distribution might be some continuous distribution on images, but when you sample from this data set, you're just getting something which is discrete. And many times you'll do uniform sampling from the data set to get a good approximation for what the underlying distribution might be. But sometimes you might also do something more sophisticated than that, with good reasons.
I see. Thank you.
Okay. So we have this sample so far, right? And we also have these labels, which we are assuming are coming from f star of xi. Okay. And in the setup that we discussed so far, the labels were exactly f star of xi, right? But once again, in the real world, when you collect data, there will be some noise, right? There might be some wiggle room. Just imagine you're trying to measure the height of every person, right? Maybe your height is only accurate within up to 1 inch or 2 inches, right? Maybe the person was wearing heels that day or was not wearing heels that day, right? So there could be some error even here. Okay. So in the PAT model that we discussed, there was no error in the labels. But the whole setup can actually be extended to the case with errors, and you can define prediction accuracy and all those things here too. But that's not something that we are doing. Again, it goes back to foundations of statistical machine learning that we are not touching in this course. Okay? But when we formulate it in this learning as optimization framework, we won't have to dig deeper into where these errors are coming from. So, and our goal is so these are our input, and our goal is a good prediction function h. And we also have an assumption on where this unknown function is coming from. Okay. So the key word here is good. How do I quantify good if I don't know what my underlying distribution D is? What should I do if I don't know what my underlying distribution D is?
You could use a metric like accuracy or something to determine if like on your examples, like your test examples, in order to determine if your model is predicting well or not?
So again, we're thinking of training and test, but we don't know what test is, right? So imagine I just had my data set. That's the only thing that I'm starting with. So what should you do then?
Okay, so then you would check on your training set then, like
Right.
your measure of
Right.
accuracy.
Exactly, right? So somehow it seems like silly, but it also makes logical sense, right? Because I don't know what my future examples are going to be. And just to try to come up with what a good prediction edge is, it makes sense to look for something that at least does as well on the training examples, right? So I can say, let me refine this goal to say, find a predictor. Let me use one keyword here. That does well on the training set. And I was going to ask, what would it mean to do well? And someone already answered the question, which is, okay, some sort of loss function, right? And this point came up even before that, I don't necessarily want my label to, my prediction to exactly equal my label, right? So sometimes if these are real numbers, that's just way too strict. So we can measure how close my prediction is. What's the quality of my prediction to the label, okay? And this is especially important when we ourselves anticipate there being some noise in my labels, right? If my label, my dataset itself can have some errors, I should also allow for some errors in prediction. Otherwise, I will be overfitting and things like that. Okay. So the way to quantify this is to do loss function. So it's some function. What should its input and output be? You should think of it as a way to score your prediction.
The data and its label.
Definitely, but we are going to do something even more rudimentary, right? I'm already telling you what the predictor is.
Okay.
And
the hypothesis, your hypothesis, your prediction function.
Right. And even more basic is almost all of ML, you first decide how to compare two predictions. Right, I have X and I have my X1, I have my Y1, and my current prediction algorithm maybe said, okay, the label should be H of X1. Okay, and I want to check how good is H on my example X1. So how do I check that?
You take the difference between H of X and F of X.
Right, so, or Y1, we don't know what F is, right? So we'll take, I'm trying to judge how good my prediction is for this example. So I'm really trying to do what is being suggested already in the chat and so on, but I'm trying to break it up into smaller and smaller pieces that we can handle. So one suggestion is to kind of check how far is H of X1 from Y1. Far could be difference, but it could also be something else depending on the context, okay? So the way this comes up is in trying to design a loss function, which takes two labels. It could be, if it's real number, it could be absolute value, it could be square, it could be something else. If it's cats and dogs and if it's a discrete set, you might say, okay, just tell me whether they're equal or not. And even in the discrete case, sometimes you might use something not just equality, okay? So it's a number, it's a function which takes two predictions, the outcome of the predictions, and tells me how close or far they are, okay? And typically you should think of as telling how far they are. So if L is 0, that means it's good for us. My prediction is close to the truth, and so on. Okay? And so let's say now that I tell you this is my metric for measuring how good my prediction is, and you can say, okay, our goal is find H such that I look at my loss over my entire data set. So I want my total loss, not just on a single point, but on my entire training data set to be small. What would I write down here then? Okay, exactly. So once again, we don't know what f is, right? So we'll just use the yi, the label, as this. I say, we don't know what f is, but we could have used f star of xi, but sometimes there could be noise. So we'll just use yi. So we are almost at a very concrete computational setup, which after that we can forget about where this computational problem is coming from and just focus on solving that. So I'm saying, okay, you have this data set x1, y1, x2, y2, which was generated, someday, I don't care how, so, from now on. But I have this goal of me. You also told me what the loss function is, and I want to minimize this. Loss of h of xi, comma yi. Is this enough? If I just tell you this, what's an easy way to solve the problem? Go ahead. Optimize, but there's also a silly way, right? You should think of this loss function as something almost non-negative. Like, if it's 0, that means it's very good. So as stated, the silliest way to solve the problem is to build a database, right? I'll store all of these values, and my L is defined as, my H is defined as h of xi equals yi. We know what yi's are, and every time you ask me, I just go into my database and pull out the yi. Then my loss is 0. Yeah, I solved the problem, but is this useful in any way?
No, because you don't generalize.
Because you don't generalize, right? Or more concretely, that gives me no information on what to do on future examples. There's nothing. It's just saying, okay, on the past I know what it is, but in the future it's completely useless, right? And the way this is quantified is saying find a simple predictor. I don't want my h to be some complicated lookup function, okay? And so in particular, just as we assumed that the true function, some of the true labels were generated from some hypothesis class, we'll also want our prediction to be from some simple class. It could be the same hypothesis class, or it could be something else. But we want it to be something simple, something that we can reason about for future predictions. Okay? So here we have parameterized hypothesis class. Okay? So meaning, there is some parameter space theta, right? And for every element from this parameter space, we get a predictor, h theta. And you can think of this parameterized class as, could be just a hypothesis class, it could be a deep neural network, it could be whatever, right? It's some parameter space, and there is some art in picking what this parameter space is. It's very important. We'll get to that later. But now, if I tell you that, okay, my hypothesis, my prediction cannot just be anything arbitrary, it should be something reasonable coming from this space, which I think is a good fit for where the truth is. What should my goal now be? How can I reformulate my optimization goal with this assumption that I have some underlying hypothesis class? So instead of just straight up looking for minimizing the loss function, I look for the parameters that minimize my loss function, right? So pretty much our goal from now on, for the netlist, the next few lectures, is going to be the following. Find the parameters that come from your assumption about where the hypothesis is. Okay, so this now is a very concrete optimization, concrete computational question. You gave me as input x1, y1, x2, y2 your data set. I made an assumption about what the parameter space is. There is some art involved in picking the right space. And after that, I have to find these parameters or the hypothesis class. I mean, parameter sounds like a confusing thing, but you should really think about it as making some assumption about what you want to output, right? I don't want my output to be a dumb lookup because that won't be useful at all for future, right? I want my prediction to have some structure in it so that I can argue about how it's going to do in the future, which is generalization, okay? And so this problem is very important and it has a name. It's called empirical risk minimization. Or ERM. Okay? It's a very important way of looking at our learning problems, right? So it has now become a concrete computational question, except there is a lot of art in figuring out what parameters to use and also, as we'll see, on how to solve this computational problem. But at least now we have a concrete question that we can use our algorithmic chops on. Right? Any questions about this setup?
A risk here refers to the value of the loss function, right?
Yeah, so it's kind of, yeah, I think that's where the term comes from. Risk is the loss of h theta of xi comma yi. Somehow, maybe the reasoning was that if I predict based on h theta, how far am I from the truth? And that's how they're saying how risky is this prediction compared to the truth. And it's called empirical because you're doing it on the samples that you're seeing, right? And there's also something called population risk minimization where you try to minimize this in expectation and so on. But when we say empirical risk minimization, this is what it means. And almost all machine learning applications have at their core some way of solving this problem. Okay? And what we'll do in the next 4 lectures is talk about the ways of addressing this computational question. This is now a minimization problem. There's some art, I mean, there's some very important gaps in how we design data and how we can reason that, okay, if you solve this problem, what does this mean? Does this solve my approximation question? Will it generalize? Will it work well in the future? Okay, that's all important, but let's first things first. Can we even solve this question? When can we solve it? What are some tricks and tools that we can use for it?
And does the solvability of this problem depend on those functions that you choose in the form of them?
Yeah, definitely. I mean, that's an important question too, which is, we want to kind of strike the right balance, right? Why can't I just choose theta to be the hypothesis class if I even know what it is? Sometimes you want to do that. In fact, that might work the best in terms of theoretical guarantees. But then the problem becomes too hard to solve. So there's a very important interplay between choosing a very complicated hypothesis class and a simple hypothesis class. And there are two things that show up here. If you take it like a traditional machine learning class, they'll talk about this bias versus variance trade-off. And what that means is roughly like, somehow if you choose a very complicated parameter space, it might not work well in the future. But it might also lead to other problems, which is that it might change your computational problem significantly. It might make easier or your problem harder. And it depends on the specific class theta that you choose. It's not clear that if you just choose a complicated class, the problem becomes harder. Sometimes it might even become easier to optimize on.
In Professor, this class of theta comprises both the model parameters as well as the hyperparameters, or is it?
So that's a good question. So here it's meant to capture only the parameters. And this distinction between model parameters and hyperparameters we'll talk about in the next lecture when we start talking about how do you solve this thing. But the main thing to keep in mind is that this is meant to capture the model parameters. And one way to think about it intuitively is that the hyperparameters are really helpful, are meant for you to solve this problem, the model parameters. And then, afterwards, like this distinction kind of blurs and you start using optimization to figure out hyperparameters and so on. But it's a different story. Okay. So in the next lecture, what we'll start out with is talking about this empirical risk minimization. Okay, we'll look at some simple cases for loss function and some simple assumptions, simple types of parameters, spaces that we can look at and play with them, what this function looks like, and then try and optimize it. Okay, and I'll end today here, but let me just do one thing, which is if you go to EdStem and if you have access to it and you go to workspace, you see this ERM workspace here. Okay, and this will make a lot more sense once we go to next lecture, but just as a build up to it, you can in your free time just run this very simple toy examples where you can see what's happening here is I plotted this loss function for the case of least squares regression. You can see this is the contour plot, and we'll play with this in the next lecture, but if you want a heads up, you can start looking at it already. Okay, and once again, this is on EdStem under workspaces. All right, in the next lecture, we'll talk about this ERM, we'll look at some simple cases, we'll do some toy examples, and then try and develop a theory on when and how to solve these problems. Okay? All right, I'll see you all on Wednesday.
Thank you.